Hey guys, and welcome back. Today we are going to start talking about chemical compounds and ionic bonding. So if you haven't done your ion lesson or your Lewis dot structure valence electron lesson, you will be completely and totally lost here. So make sure those are done and completed before you move on to this lesson. But if you are all caught up, and you have done those, then we are ready to move on to ionic bonding. And here's just a little chemistry cat joke for us. My name is Bond. Ionic bond. Taken, not shared. And the reason this joke will become obvious at the end of the lesson, but basically ionic bonds are when electrons are transferred between elements, and that's why it says taken, not shared. But yeah, this joke will become a little bit more obvious later on. So first and foremost, we have to define what is an ionic bond. Ionic bonds are composed of metal cations and non-metal anions. So remember, you guys already know how to identify metals and nonmetals. Remember, our metals are on the left-hand side of the periodic table, and our nonmetals are on the right-hand side. Our metals will donate their electrons, so they will get rid of those negatively charged electrons, thereby becoming positive, which we know are cations. And then our nonmetals will then take on those electrons, which are negatively charged, and of course those will become anions. Now, even though ionic bonds and ionic compounds are composed of ions, they are electrically neutral, okay? So the total positive charge will equal the total negative charge. So even though the ions on their own will be charged when they're together in a compound, remember, a compound are two or more elements bonded together. When they come together in an ionic compound, the charge of the compound itself will be neutral, kind of like a neutral atom. So we know in a neutral atom that the positive protons and the electrons equal out the charges. In an ionic bond, the charges of those elements are going to equal each other out, and overall it is going to be neutral. And then these are just some examples of these ionic bonds that you guys are going to get familiar with over this unit. So what are the properties of ionic bonds? They are formed by a complete transfer of electrons, okay? So the electrons are going to go from the metal to the nonmetal. So they're given those electrons over. They're made up of metals and nonmetals. So if you had a question that said, okay, will these two elements form an ionic bond? If one of them is a metal and one of them is a nonmetal, then yes, it will be ionic, okay? Now there are different types of bonds, but today we're just focusing on the ionic bonds. They are solid at room temperature, and they typically have a high melting point, and they're good conductors of electricity. Okay, so that means it takes a lot of thermal energy to melt them. So to form the ionic bond, the cation, the metal cation, will completely transfer its valence electron to the non-metal anion. Okay, so here we have sodium and chlorine. This should look familiar to us because we've done Bohr models and Lewis dot structures. So sodium is sending his valence electron over to chlorine. Okay, he's completely transferring his electron over. And again, here's that representation. So lithium has one valence electron in his outer energy shell. Fluorine has 7 electrons in his outer energy shell. And when we form an ionic bond between lithium and fluorine, that electron, that valence electron from lithium, is going to be totally transferred over to fluorine. So lithium would be the cation, fluorine would be the anion, and this is a total transfer of electrons there. Remember, it's going to go from the metal cation to the non-metal anion, okay? And then our result would be lithium fluoride, which we'll talk about naming a little bit later on, but we would have one atom of lithium and one atom of fluorine, okay? Now, how we know the formula, right? How would we be able to tell the formula? I'm going to teach you here in just a few minutes, but to be able to determine the formula, remember the charges have to cancel out, okay? So when we're looking at elements that are going to come together to form an ionic bond, we have to be able to determine the charge from the periodic table, which you know how to do because you know about ions and you know about valence electrons. So you have to determine the charge of the cation and the anion, and then you have to set up the formula so that those charges balance out, okay? Here, lithium is a +1 cation and fluorine is a -1 anion. So it only takes one of each to cancel that out. So its formula unit is just 1 atom of lithium and 1 of fluorine. Okay, but I'm going to teach you a method to do that here in just a few. So when multiple ionic compounds combine, they form a structure called an ionic lattice, where each ion is surrounded by ions of opposite charges. Okay, so like here we have our sodium and chlorine. These are ionic bonds, so these would be multiple ionic bonds, right? This is a lattice structure of those ionic bonds between our, again, metal cation and our non-metal anion. So then how do we tell the formula? Like how can we tell how many of each atom is there and how many, what the actual formula of the ionic compound is, okay? Here's how we break it down. You guys are going to have to get comfortable with writing these, not only writing them, eventually naming them, and then figuring out what the composition of the compound should be. So anytime we have a compound, remember we'll have 2 or more elements, okay? So we know by this point the chemical symbols tell us what element they are, right? So Ca is going to be calcium, and then Br is bromine. We can find those on the periodic table. Remember, elements, single elements, are going to be at least 1 capital letter, and if it has a second letter, it will be lowercase, right? So we know that these are 2 separate elements here, okay? The subscript tells us how many atoms of the element are in the compound, right? If you do not see a subscript, we assume that it's 1, okay? We don't include ones as sub or superscripts just because it's assumed. So here in this example, it would be 1 atom of calcium, 2 atoms of bromine, okay? So this would be an ionic compound because calcium is a metal, bromine is a nonmetal, so we know it's ionic. Then we know that there's 1 atom of calcium because there's an assumed 1 here. And then we know there's a superscript of the 2, so we know there's 2 atoms of bromine. And then here's some different examples as well of ionic bonds and their composition. Here we have aluminum and bromine. We would have 1 aluminum atom, 3 bromine atoms. Here we have potassium and sulfur, 2 potassium atoms, 1 sulfur atom because again, this 1 is assumed. And then we have magnesium and oxygen, 1 magnesium and 1 oxygen, okay? So that's how we can determine how many atoms, right? And we'll go over naming, but this would be aluminum bromide, potassium sulfide, and magnesium oxide. So those would be the names of those compounds. So how do we know? So like, how do you know that you only need 1 magnesium and 1 oxygen in magnesium oxide? Like, how would you be able to determine that? Well, remember, our goal is to make a neutral compound. So the positive and the negative charges must cancel out, okay? So that's why I said if you haven't done your ion or your Lewis dot lessons, you're going to be lost here because you have to be able to determine the oxidation states from the table in order to successfully create your compounds, okay? So remember, our metals are going to donate those electrons. We know the valence electrons based on the group number. So our alkali metals are group 1, which means they have 1 valence electron, which means they're going to donate 1 electron, which means they have a +1 charge, okay? So remember, these oxidation states right here, those are not the number, it is the number of, not the number of valence electrons, but the charge, right? So, because like, remember in group 17, they have 7 valence electrons, meaning they want 1 electron to fill that octet rule to make them stable. So if they gain 1 electron to get to 8, that means they're going to take on one electron's negative, which is -1, okay? If everything I said was totally Greek to you, go back to your ion lesson and review that, okay? So, again, when we're doing this, we need to first determine the number of valence electrons in each element in the compound, determine its oxidation state, and then we can determine the actual formula, okay? And this, of course, you guys have access to the slides, so this will be a cheat sheet for you. Again, these are the charges for each anion or cation, not necessarily the valence electrons, right? These are the charges that happens when those valence electrons either get donated or more electrons are taken on. So how do we do this? Number one, you have to find the element or the compound. If it ends in "ide," it's on the periodic table of elements, and if it ends with "ate" or "ite," it's a polyatomic ion. We're not worrying about polyatomics today. We'll do those a little bit later. So actually, we're not even going to worry about the compound itself because I'm going to give you guys the actual elements today, and we'll talk more about naming and then polyatomics tomorrow and a little bit later on. So all you guys have to do today is, number one, determine the charge of the ion, and then you're going to swap, drop, and chop those charges, okay? Don't even worry about the transition metals. I probably should have taken this slide out because I was going to break this down. But basically, we're swap, dropping, and chopping the charges. So we're going to swap the charges of each individual ion. We are going to drop the charges to the other element in the compound, and then we're going to chop, which means to simplify the subscripts. So like if you've got 2 and 4 in your subscripts, those can be simplified by a factor of 2, okay? So how do we do this? Here are our examples. So this is the extent of what you have to do today. I'm just going to give you elements, and you are going to have to determine the charge of them and then determine what their ionic compound would be, the formula of the ionic compound, okay? So first thing we have to do is swap, right? We have to swap our superscripts for our subscripts. So in this one, the 2+ is going to come to this side, and the -1 is going to come down here to be the subscript of calcium. So the +2 goes to the bottom of fluorine, and then the -1 goes to the bottom of calcium, okay? So we swapped the numbers. Then we're going to drop our charges. So we're going to get rid of the plus and the minus, okay? So what that means is, I'm going to get a little pencil here. So we're going to have calcium, and this 1 came down here. Now we don't do subscripts for 1s because they're assumed, so we're just going to leave calcium alone. And then we have our fluorine here. This 2 came across, right? We swapped, dropped, and chopped, and we're going to have a 2 there. Okay, so that is your ionic formula for calcium fluoride. Okay, so again, all you have to do is take the charges, take the numbers, take them from the superscript of the first element, and add them as the subscript of the second element. We're going to drop the charges so you don't have to worry about the plus or the minus. And then chop is simplified. This is as simple as it can get because we have a 1 and we have a 2 here, so that's already simplified. Okay, so let's do the next one. First, we're going to swap, so we're going to take this 2 down this way, and we're going to take the 3 down this way. Okay, this is also called the crisscross method. So swap, drop, chop, crisscross, whatever you want to call it. But here we'll have magnesium. And we're going to drop the charges. So the 3 came down here, but we don't want that minus, so it's just going to be 3. And then we have nitrogen. And this 2 has come down here. And again, we drop the charges. So Mg3, so 3 atoms of magnesium and 2 of nitrogen. So now that we've done the first two examples, or I've done the first two examples, go ahead and try to do the last one on your own. So you have aluminum and phosphorus. So in your